In this module, we want to start looking at some organic molecules. You need to start memorizing these molecules like the base functional group. You will get exposed to it again in second semester chemistry, but if you can memorize them now, it'll be easier when you come back to second semester, and you are responsible for them this semester. As a reminder, organic compounds are mainly composed of carbon and hydrogen, where we'll find oxygen, nitrogen, phosphorus, sulfur, and trace amounts of other elements there as well, but organic chemistry really is the study of carbon chemistry. If you take all the molecules, all the compounds in the entire world and put them in a pile, if you put anything that contains carbon in one pile and anything that does not contain carbon in a second pile, the pile containing carbon-containing compounds or carbon-containing molecules would be bigger than the other pile combined. Carbon's it's in everything that's living. So it's a very important molecule. It does some really important chemistry, and you need to start identifying these functional groups now so that you're better prepared when you come to your next classes. So general rules we're going to follow: write the skeletal structure for the molecule, calculate the total number of electrons for the Lewis structure by summing valence electrons of each atom in the molecule, distribute electrons, giving octets or a duet for hydrogen to as many atoms as possible, and form double or triple bonds as necessary. Now, these are the rules we do follow. Do we follow them specifically? It depends. If we're given the formula, yes, we follow these rules. If we're given the name, we use the name to tell us how to put the compound together. So if you're given a formula, you want to follow the rules. These rules follow the same things we've already been doing for Lewis structures. So same patterns, same everything. This time you're just adding up lots of things instead of probably a smaller amount of things, meaning more atoms adding up and seeing how they're all connected. You'll start to see patterns. We'll see carbon likes to bond to itself a lot. We'll see that hydrogen likes to bind to carbon, but only one bond for hydrogen, remember that. Hydrogen will bond to oxygen just as well. We'll see that carbon wants 4 bonds, if it can have it. Oxygen wants 2 bonds, 2 lone pairs. Doesn't mean it always gets its way, but that's what it prefers. Hydrogen, 1 bond. Nitrogen, 3 bonds, 1 lone pair. So what we talked about in the previous module about how to tell if it has a 0 formal charge, and just memorize that these are the patterns. Second period elements, so oxygen, nitrogen, carbon, these are not in order, obviously, fluorine, these never have an expanded octet, so they can never have more than a combination of 8 electrons between bonds and lone pairs. Remember, a lone pair is 2 electrons. A bonding pair also counts as 2 electrons, even if they're shared. So naming straight chain hydrocarbons. Straight chain just means that they're forming a straight chain. It's carbon, 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 carbon. We then take that molecule and we add enough hydrogens to it to give every carbon 4 bonds. Carbon wants 4 bonds, so we're going to give it enough hydrogens to give it 4 bonds. That is a straight chain hydrocarbon. Specifically, I have 1, 2, 3, 4, 5, 6, 7 carbons here, which means I have heptane. So we'll talk more about these in just a sec, but the ending of the name, ane, for alkane, this means all single bonds. Ene for alkene means that you have a double bond present. There could be more than 1 double bond, but we'll go into that in second semester chemistry. For this semester, you can assume there's 1 double bond somewhere. Ine for alkyne means there is a triple bond. So, double bond. This is ethene. Triple bond. This is ethine. And if it was a single bond, And note each time I'm only giving it enough hydrogen so that the carbon has 4 bonds. This is called ethane. So you're going to have to memorize these bases. Meth for 1 carbon, eth for 2, prop for 3, bute for 4, pent for 5, hex for 6, hept for 7, oct for 8, non for 9, and dec for 10. The other thing we do is we put an ending to the name that tells us the type of functional group it has. A functional group dictates the type of chemistry a compound will undergo. So hydrocarbons mean carbon-hydrogen containing compounds. Alkanes, single bond. Alkene, double bond. Alkyne, that I need to fix this slide. I keep forgetting, should say triple bond. So again, if I say ethene versus ethane versus ethyne. So note that what's highlighted here, or what's bolded, is what I put as the ending name. Let's see if I can get in there. So ane, ene, ine. Aromatic compounds, this is an aromatic compound, have alternating double and single bonds. This is called a benzene ring. If you have an alcohol, we would end the name with OL. So ethanol. This is ethanol. This is the formula of ethanol. And alcohols have a structure where they have an R group attached to an OH. The R stands for the rest of the organic molecule. R prime can be different from R. But note here, this is just a carbon-hydrogen containing compound with an OH on the end. That is ethanol. We said eth was 2 carbon, eth, and all. It's like ethane. We just make it sound actually full name. And we have an OH group on the end, an alcohol group on the end. We can have ethers. These R groups here may or may not be the same. They don't have to be, but they can be. This is called dimethyl. There's an L there. Ether. Methyl, methyl with an ether. Notice an ether has an oxygen sandwiched between the 2 R groups. Aldehydes end in Al. So for an aldehyde, I have a carbon in the center that's double bonded to an oxygen, single bonded to an hydrogen, and then has an R group to the side. What that R group is could be anything, but an aldehyde is uniquely identified by this group. This carbon double bonded to an oxygen with a single bond to a hydrogen. This would be ethanal. I've got 2 carbons and I've got an aldehyde. Ketones, and with ONE. Ketones and aldehydes are very similar. The difference is that a ketone does not have a hydrogen off that carbon, it has another carbon. So here, notice there's no hydrogen connected to that carbon. It is still double bonded to an oxygen though. Methyl ethyl ketone. I have a methyl group, I have an ethyl group, I have a ketone. Carboxylic acids. These are acids. They have a functional group that looks like this. They have an R group attached to a carbon, double bonded to that oxygen still, but instead of an H or an R group here, we have an OH. That OH, this is what makes it acidic. It loses that hydrogen to make it acidic. This is acetic acid. And we usually leave that IC on the end of the name as well. Esters end in O8. An ester is very similar to an carboxylic acid where we have the carbon double bond to the oxygen with an O here, but instead of an H, we have another R group here. methyl, I can't spell. OH. A methyl group, an ethyl group, and an ester in the middle. And amines mean you have a nitrogen-containing compound. So nitrogen, nitrogen, nitrogen. I would call this one methyl. Got a methyl group here. Amine. I'm not so worried about you naming them as much this semester as I am about you starting to recognize these functional groups. You need to be able to recognize if I give you a base structure like one of these. So if I give you a structure like one of these, can you name them? Can you not name them, but can you write the Lewis structure? Can you also start to identify the type of functional group they have? Let's work a few examples. Big thing to remember here, carbon always has 4 bonds. If we give carbon its 4 bonds, it makes it easier. So in naming, we don't always specify that carbon has 4 bonds. We give the compound whatever the name tells us, and then we give it enough hydrogens to make it neutral. So first, let's look at butane. It says 1 long chain of carbon atoms. Bute tells me 4. Ane tells me single bond. 1, 2, 3, 4. I'm now going to give this enough hydrogens to make all of the carbon atoms have a 0 formal charge, meaning all of them need to have 4 bonds total. The 2 ending or terminal carbons will each have 3 hydrogens to it because they're each bonded to 1 carbon, and the 2 internal carbons will each have 2 hydrogens because they each have 2 bonds to carbons. How about ethanol? Eth tells me 2. Al tells me alcohol. So I've got 2 carbons with an alcohol group. I'm then going to give those carbons enough hydrogens to make them have a 0 formal charge or have 4 bonds. Propanoic acid. Prop, 3. Oic acid, carboxylic acid. I have 3 carbons and then a carboxylic acid. That last carbon will be single bonded to an O, which is single bonded to an H. That's my alcohol, or this is my acid. This is the proton that's lost. This whole group is my acid group, truthfully, but, oops, too far. This is the proton lost to make an acid. Or why, not to make an acid, but it's the proton lost, which is why the compound is an acid. Donated. But I need to give those carbons enough hydrogens to make them neutral. Well, this carbon already has 4 bonds, so it doesn't need any hydrogens. But this one needs 2 hydrogens. This one needs 3 hydrogens. And that is propanoic acid. An ether with 2 carbons. Ether means that I have an oxygen sandwiched between carbon atoms. It tells me 2 carbons. Well, I got to have 1 on each side since it's an ether. By definition, it has to have an oxygen in between 2 carbons. Ethyne, eth meaning 2, ine meaning triple bond. Carbon triple bonded to itself with enough hydrogens to make it have a formal charge of 0. And propene. Prop meaning 3, ene meaning double bond. Where do I put the double bond? It doesn't matter. Pick one. And then give the carbons enough hydrogens to make it neutral. I could have also written the double bond on the other side. You'll note that these molecules are completely equivalent. I could just flip the molecule around and get the same thing. So go ahead and practice these. Practice trying to identify, trying to write these out based on their names. If you're given the formula, it's a little bit easier because we write them the way they're connected. So like ethanol, we write CH3, CH2OH. It's connected the way it's written. You guys always see me write acetate as CH3COO minus. And that's because it's C. Let me find space here. It's carbon with 3 bonds to hydrogen, CH3, C, O, O with a minus charge. Acetic acid, CH3COOH, same type of setup. The carbon has 3 hydrogens bonded to it, bonded to another hydrogen or another carbon, which is double bonded to an oxygen, single bonded to an oxygen, and bonded to a hydrogen. So they're written out the way they're connected. Also work on this chart. Try to start memorizing these things. The main structural feature. This will help you a lot. Again, this comes back pretty heavy in second semester Gen Chem.